Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 3. Newton's Interpolation Formulas for Uniformly Spaced Data. Using interpolating polynomials suited especially for a set of uniformly spaced datasets not only simplifies formulations but also reduces the CPU time considerably. Consider a set of uniformly spaced data xk, fk for k equals 0, 1, through n. We make use of the forward, backward, and central difference operators covered in Chapter 5 to obtain a more compact form for the interpolation formulas. Recall the following definitions. Consider a uniformly spaced dataset. We wish to interpolate for an x value within the interval from xk to x, k plus 1. Newton's divided difference formula for the coefficients for any x in the interval from xk to x, k plus 1, reduces to substituting a's into the interpolating polynomial yields Gregory-Newton forward difference interpolation formula, where s is the interpolation variable defined as x minus xk over h, and the term in parenthesis denotes binomial coefficient. Likewise, an alternative interpolation formula, the Gregory-Newton backward interpolation formula, can also be constructed by using backward differences as follows, where s is the interpolation variable defined as x minus xk over h and sm in parenthesis is the binomial coefficient. The Stirling formula is used along with the full lines, while the Bessel formula uses the central differences along the half-lines. Stirling's formula for full lines is given as follows. Bessel's formula for half-lines is given as follows. Forward, backward, and central differences are obtained from generated tables. In central difference tables, a new line in plain background between each line of data with highlighted background is inserted as shown here. Blank spaces are filled as the arithmetic average of the entries above and below. We can predict whether a set of discrete data is smooth or not by inspecting the entries of a difference table. If the discrete function is smooth, the successively higher differences along the chosen baseline will become smaller and smaller in magnitude. A high-degree interpolating polynomial in such cases will produce very accurate estimates. The Gregory-Newton forward or backward interpolation formulas are used almost exclusively for interpolations near the beginning or end of a table, respectively. These formulas may not be suitable when interpolating for x values near the middle of the tables. For such cases, interpolating formulas that make use of central differences are preferred. A central difference table is similarly constructed by using the central differences. We define the lines containing the original data as full lines and distinguish the new lines from the full lines as half-lines. It may be tempting to add as many terms as are available in the Gregory-Newton interpolation polynomials to obtain the most accurate approximation. If the discrete function is not smooth, adding up all or most terms does not guarantee improved accuracy. Adding each term in the interpolation polynomial increases the degree of the interpolating polynomial by 1. For instance, for the backward interpolation formula, we may write 2-term sum is linear, 3-term sum is quadratic, and 4-term sum is cubic polynomial. Once the difference tables are constructed, any suitable interpolation formula can be used to find interpolates. For a smooth function, best estimates can be obtained with a baseline that has a large number of entries. For a non-smooth function, the use of a high-degree interpolation polynomial is not advised. Asterisk in the table entries indicate numbers that do not necessarily have the same value. A simple guideline for selecting the optimal baseline is to choose the line in the table closest to the interpolation point so that the resulting value of S is the smallest, provided that the higher differences are decreasing in magnitude. Generally, if the value to be interpolated is in the highlighted region at the top of the table, the forward difference interpolation formula is preferred. In the highlighted region near the bottom of the table, the backward difference interpolation formula is applied. Or in case of interpolations for x values near the middle of the dataset, any suitable central difference interpolation formula can be used. The error bound for an nth degree interpolating polynomial, p in x, can be obtained using the error bound from the Newton's divided differences. The order of magnitude of the approximation error, absolute value of e in x, is about the next difference not used in absolute value of p in x. The error term in S variable is an nth degree polynomial with decreasing magnitude near the interval endpoints. Since the error is proportional to h to the n plus 1, the magnitude of the error decreases for h less than 1 with increasing n. If n plus 1th derivative of fc grows larger with n, the magnitude of the error decreases only if h is sufficiently small. Consider an error of epsilon in a tabular value, and assume all data in the set are correct except for one that is an epsilon error. The isolated error is magnified and spread out in a triangular pattern as higher differences are generated. The largest error occurs in the same row as the erroneous value. Also, the algebraic sum of the errors in any column is 0. The method has the same advantages as Newton's divided differences. They require fewer arithmetic operations and less CPU time since they are derived specifically for uniformly spaced data. For smooth distributions, the convergence or accuracy can be monitored by the absolute value of Pn minus P, n minus 1. As a method, it is no different from Newton's divided difference. They can only be applied to uniformly spaced discrete functions. Now we consider the following discrete dataset for which we will derive the forward, backward, and central difference tables. And then, we will use the suitable interpolation formulas to estimate f1.2, f2.1, and f2.9. We reserve the first column for the indices. We place the abscisses and the ordinates in the second and third columns of the table. The first forward differences are placed in the fourth column, which are calculated as the difference between consecutive values in the f values in the third column, except the last one. The procedure is carried out for each row as follows. Now, we move on to compute the second forward differences, which are the differences of the first forward differences, and place them in the fifth column. The process is carried out as follows. If necessary, which is the case in this example, we continue to calculate higher-order forward differences until we get a single difference value in the last column. The third differences are placed in the sixth column, and the fourth difference is computed and placed in the seventh column, which completes the construction of the forward difference table. Constructing the backward difference table is similar to constructing a forward difference table. We reserve the first three columns for the index and dataset. The only difference is that the first backward difference is obtained, as illustrated, by differencing the prior value from the current value of the row. That is why we start with the second row and compute the first backward differences for each data point, except for the first one. The results are placed in the fourth column. The second backward difference is the difference between consecutive values of the first backward differences. Starting with the second row, we compute the second backward differences and place the results in the fifth column. We compute the third and fourth backward differences and place the results in the sixth and seventh columns, respectively. A central difference table is constructed using the central differences. A new line between each line of data, depicted with a highlighted background, is inserted. Then, we define the lines containing the original data as full lines, and distinguish the new lines from the full lines as half lines. We fill the blank spaces on half lines by simply taking the arithmetic average of the values above and below each blank space, as illustrated. The first central difference is computed using the values in the third column and written in the fourth column, exactly halfway between the two lines of values involved, as shown. However, we end up with blank spaces on full lines, which are filled out by taking the arithmetic average of the values above and below each blank space. This differencing procedure is repeated for the subsequent columns by using the values of the prior column. After placing the central differences, each column, yet, will contain blank spaces on either half or full lines. These blank spaces are filled out in the same way by taking the arithmetic average of the values above and below each blank space. Now that the difference tables are ready, we can move on to carry out interpolations. To obtain f1.2, we will use the forward interpolation formula. Since the point x equals 1.2 is closer to the row x equals 1, which has the largest number of table entries that are also decreasing in magnitude, the interpolation variable s becomes 0.4. The baseline, x0, is selected as the line x equals 1. We use the forward difference interpolation formula as follows. With the baseline values are f0 is equal to 15, delta f0 is equal to 25, delta squared f0 is equal to 20, and so on. Substituting the numerical values into the formula, we calculate each term separately to determine their contribution to the overall result. We note that each term added is smaller in magnitude than the previous one, which leads us to conclude that fx is smooth. Hence, we can safely sum up all the terms, which gives 22.984 as the estimate for f1.2. We examine the central difference table to determine the most suitable baseline to calculate f2.1. We note that the row x equals 2.1 is closest to the row x equals 2 with the most entries, which is also a full line. Thus, we select the row x equals 2 as the baseline. The interpolation variable s is found to be 0.2. The values to be used in the central difference formula are read as f2 is equal to 85, delta f2 is equal to 58, and so on. To carry out the interpolation for full lines, we use Stirling's formula. We substitute the numerical values into the interpolation formula and calculate each term separately to determine their contribution to the overall result. Notice that each term added becomes smaller in magnitude than the previous one, which is not surprising since we earlier found out that the fx was a smooth function. Thus, we can safely sum up all the terms, which yields 96.928. To obtain f2.9, we will use the backward interpolation formula, as there are more entries in the row for x equals 3. And so, we select the row x equals 3 as the baseline. The interpolation variable s becomes minus 0.2. Notice that the row x equals 3 also has the most number of entries in the table. We will use the backward difference interpolation formula. With the entries of f4 equals 259, nabla f4 equals 103, nabla squared f4 equals 32, and so on. We substitute the numerical values into the interpolation formula. We note that each term added becomes smaller in magnitude than the previous one. Thus, we can sum up all the available terms in this formula, which gives 235.552. Recall that the third differences in the interpolation tables were 6, and the fourth difference was 0. This outcome implies that fx is a third-degree polynomial. In this case, it is possible to find the true polynomial fx using any one of the forward, backward, or central interpolation formulas. Here, we use the forward interpolation formula with all available terms. We use x0 is equal to 1 as the baseline and define the interpolation variable in general for any x. Substituting s into the interpolation formula, we obtain the following third-degree polynomial. When we evaluate the polynomial for x equals 1.2, 2.1, and 2.9, we find that the interpolated values are in fact the true values of fx. And with this result, we conclude this session. That is all for now. See you next time with another topic. Bye.